So I didn't get to see any car, any real cars, until I was about 2 years old. And this is because I was born in this small little village in the middle of Africa where we really didn't need transportation because everything was in one single place. So it was only until I was 2 years old, one of my first memories, first things that I remember, when my parents took me to the city and I got to see a car for the first time. Now, because my mom was a teacher, she used to give me all of these books. So I had seen cars on drawings. We didn't have a TV back then. So it was mainly just on drawings and books and cartoons. So I had an idea of what a car was. And I used to draw it. I used to love to draw. But then when I went to the city and I saw the cars, I was like, wait a minute. that's that's a 3D object. It looked nothing like I've been drawing it as a cartoon, right? It was in real life, and I was blown away, and I still have that memory today, right? And I'm talking about this because this is related to what we're going to be talking about today. General Chemistry 1, even in the last chapter, we learn how to draw chemicals and atoms and molecules and compounds. But one of the things that we introduce you, and one of the things that you learn once you start to learn about chemicals in real life, you realize that chemicals are not drawn as 2D cartoons, right? In real life, they occupy three-dimensional structure, just like the real cars that I saw compared to the cartoons that I've been drawing. Today's chapter, is going to be about molecular geometry. If I give you a molecule like H2O, like CH4, are you going to be able to draw it? Because we did a structure of CH2 earlier in the last chapter, but the geometry looks different, right? So let's get started. So let's say you have this molecular geometry. All right. So let's say you have, so first we're talking about molecular geometry and VESPR, VESPR. What is VESPR? VESPR is valence shell electron pair repulsion. This is how we find the geometry of a certain chemical. So this is an example that I was showing you earlier. You have, this is not methane, this is actually CH. Let me see if I can draw here. This is here we go. Boom. Boom. All right. So this is CCl4. CCl4 is going to be, if you were drawing a Lewis structure, it's going to be C in the middle, carbon in the middle, and then C it on the outside. Just remember that we gotta give Cl its electron pairs, right? Because this is a Lewis structure. Remember, this is the dot structure that we learn how to draw. But again, this is a 2D cartoon, right? In the real life, it's going to be a 3D. In fact, let me show you, because since you can do almost anything with AI now, I actually made, believe it or not, I made an app to show you this. So this is the app that I made. Okay, so, and this app will show you this. So I just made this app for this chapter. But this, you see, this is the three-dimensional structure. This is CH4, right? But you see that this is a geometry. It's a 3D geometry. right? Chemicals in nature occupy 3D space. So Vesper here teaches us how we are going to not only remember that you have 2D space, but we're going to know how to predict the 3D space, right? So it's used to predict the 3D shape of the molecules. And it's going to be based on electron pairs around the central atom. Remember that, the central atom. All right. So we're going to go through a series of examples in this chapter. And it's going to be a series of examples that are going to be centered around the center atom. What do I mean by that? I mean, let's get a clean page here. What I mean by that is that if you have a center atom, right, I think we're calling it A, center atom A, then the center atom is going to be surrounded by other atoms, right? Why? Because it's in the centers, right? So if you have like 4 things surrounding this center atom, and then you have B will be our surrounding atoms, right? Then we're going to be able to predict the geometry based on the center atom and the things surrounding it. So we're going to realize that when you have a center atom A and 4 atoms surrounding it, we're going to have a certain geometry. And this is the tetrahedral geometry that we were just looking at the app that I showed you, right? So in this app, this is tetrahedral geometry, right? But then there are others, because guess what? And I want you to pay attention to this, because this is one of the biggest take-home messages, is that if this center atom, the same center atom, if it has a pair of electrons here, right, it's not going to be the same geometry, because these pairs of electrons are going to also be electrons that are occupying space. So because of that, the geometry is going to change. So we're going to look at when the center atom doesn't have any pairs here versus when it does. And then we're going to look at the number of atoms surrounding it, right? So let's make it even simpler, right? If you have the center atom A, right, center atom A surrounded by two atoms, right? It's going to be like this. But if the center atom A has 2 electrons on it, the electrons occupy space to the point where we make an angle here. You see what's happening? The electrons occupy space and they have energy. And because of that, it's going to bend. So these 2 geometries will be different, even though it's 1 atom bound to 2 atoms. But the pairs are going to play a role, right? So this is going to inform how we find geometry. So let's start with the first level. The first level is what I was just talking about, right? So let's say you have center atom A with 2 atoms. So AB2. So there are no lone pairs. So this table, I'm gonna come back to this table a lot. In this table, you have atoms bound to the center atom and then 0 lone pairs. If you have zero lone pairs, then it's gonna be like down here. It's going to be linear, right? So you see how the arrangement of electron pairs and molecular geometry is going to be the same. Why? Because there are no pairs, no lone pairs, right? So it's linear. So an example for each one of these, I'm going to give you an example because you should be able to come up with an example. Barium chloride is linear with 0 lone pairs, right? So this is an example of linear geometry. What if you add one more? Now you have 1 bound to 3 atoms, right? This is going to be called a trigonoplanar. Trigonoplanar means triangle, means 1 atom in the middle, right? A in the middle, bound to B like a triangle. You still with me? All right, so that is going to be how we are going to measure 1 atom bound to 3 atoms with no lone pair. One thing that I want you to realize, guys, is that one of the principles that we're using is what we call stability, right? So if we have 3 atoms surrounding 1 atom in the middle, they're going to just push away from each other to the point where they are like at equilibrium at equal angles. So angles matter here. Angles, I will be asking you angles, right? So that's why I give you angles here, because I will be asking you like, hey, if you have a trigonoplanar, what angles do we have? This one, each one is 120, right? So they spread nicely so that each angle is 120. An example is BF3. So this is trigonoplanar, not planar. It's trigonoplanar. It's planar because it's flat, it's on one plane. Trigonal because it's like a triangle. And then an example is boron trifluoride. All right, so let's go to the next level. The next level is A bound to 4. This is the example that I already given you, like CH4. This is going to be a tetrahedral. Tetrahedral is the one that I was just showing you on this app, where 1 atom is bound to 4 atoms, and you see that they are also pushing away from each other in 3D space, right? So this is a tetrahedral. What's the angle for a tetrahedral? 109.4, 109.5, I mean, for all of them, right? So this is an example is CH4 or methane. What about 5? 1 atom bound to 5 is called trigonal bipyramidal, right? Trigonal bipyramidal. I want you to remember this. Trigonal bipyramidal, how? Is because you have a trigonal. Remember, trigonal is triangle, and then you have a pyramid on top and the bottom. Maybe this will help you here if you can visualize it here. Let me see if I can find the trigonal bipyramidal. This is a trigonal bipyramidal, right? So it has a triangle in the middle, right? Triangle in the middle, and then a pyramid that will be on the top and the bottom. So the example is PCl5, right? Or phosphorus pentachloride. Trigonal bipyramidal, because we need to remember the angles. The trigonal part in the middle has angles of 120, and then the vertical angles will be 90 degrees Celsius. Trigonal bipyramidal. 1 atom bound to 5 atoms, right? The next one is 1 atom bound to 6 atoms. We call this an octahedral, right? So it's going to be like this, an octahedral. So it's four, like a square with an atom at the bottom and at the top. It's called an octahedral. Pretty cool, pretty uniform. Octahedral. A lot of people like this shape. And the angles will be 90 degrees across the board, right? So sulfur hexafluoride is an example, SF6, right? So these are those angles, right? So that's the tetrahedral. Now that we looked at this, guys, I want you to pay attention. I want you to stay with me here. All of these from one middle atom bound to 2 to 1 bound to 5, we have not introduced base pairs. So now we're going to see how does it look like when it has base pairs, because the geometry changes, right? Starting with, yes, you have A bound to, so AB3, as you remember, AB3 is trigonoplanar, right? But look at this. AB2E, E is pair, right? Think of E as an electron pair. So that means you have A here, right? But you have B here, you have another B here, but then the E is an electron pair. So you have an electron pair here, right? I want you to stay with me here, because this compared to the other one, right? The other one is B here, B here, B here. So this is AB3 trigonoplanar. But this one is AB2 with an electron pair. So the geometry is a bit different. But another important thing that I want you to remember is this. The arrangement of electrons, or what we call the electron geometry, right? Electron geometry. The electron geometry here is still trigonoplanar, because if you're just looking at electrons, whether or not they are pairs, you still have a trigonoplanar shape. But then when you're looking at molecular geometry, right, this will be bent. It's a bent geometry, right? So it's called bent. It's no longer a trigonoplanar because you don't have anything at the top. So when you have one thing bound to three things, trigonoplanar. But when you have one thing bound to two things and an electron pair, it becomes bent. The biggest example of this is water, right? Water it has bent geometry. So water has bent geometry. Always remember that, right? So it's like, no, actually water doesn't have bent geometry. Scratch that. Water has another geometry that we're going to talk about. But this one, let me show you I think I have one on my app. SO2, right? SO2, very nice bent geometry. It has a pair at the top that makes it bent. So this is bent geometry. Sometimes we call it angled geometry. So this is SO2, right? So that's angled geometry. We like it. Okay, so that's when you have this. But what if we have, instead of a tetrahedral, so tetrahedral is usually one thing bound to four things, right? Well, what if one of them is a pair? Then you have trigonopyramidal, right? So usually, remember, a tetrahedral is one thing bound to four things like this, right? But if one of those is a pair, then the molecular geometry is going to be like that, right? So it's going to be a pyramid. It's going to be a pyramid with triangle legs. That's why it's called what? Trigonopyramidal. The biggest example of that is called NH3, right? N has a pair here, and then it has three hydrogen, right? So if I ask you what is the geometry of NH3, it's trigonopyramidal. You get it now? I think I have a NH3 here. You see, this is really cool. Trigonopyramidal. This is the geometry. The top is the electrons, all right? Okay, let's continue. This one is the one that I was talking about, water, right? Water is bent, but it's bent in a special way, in that water is oxygen with hydrogen here, with hydrogen here. If you remember how to draw it in Lewis structure, you remember that water has two electron pairs, not just one, it has two electron pairs. So its bent geometry, its molecular geometry is bent, but I want you to pay attention to this. Its electron geometry is tetrahedral. Why? Because it's bound to four things. It's bound to four things. So if you're just looking at the electrons, it's bound to four things. So it's tetrahedral. But if we're looking at the molecular geometry, we're looking at the actual atoms bound, which are two atoms that are bound in the bent shape. So if I ask you, like, what's the electron geometry of water? It's tetrahedral, but what is the molecular geometry of water? It's I was going to say it's H2O, but no, it's bent. Okay, so that is H2O. Very good. So what if you add 5, right? So you have 5. We say that when you have 5, it's trigonopyramidal. But when you have 5 and one of them is an electron pair, you have a seesaw. I don't know if you can see the seesaw, but it's like a swing, right? You see the swing. This is a swing. These are the legs of a swing. You can swing back and forth, right? So you take the trigonopyramidal. I don't have the seesaw, but I have the trigonobipyramidal, right? So you have the trigonobipyramidal and you remove one. So let's just say you remove the top CL. You see how the rest of it is a seesaw? See the swing, right? That's a seesaw, right? So that's why it's a seesaw geometry. All right. So now we got the seesaw. All right, let's look at a few more, right? If you have trigonopyramidal, but you add 2 pairs, we're gonna have a T-shaped, which is a literal like T, right? So you have 2 pairs here, so the rest is T, and again you have examples, right? So but you get the picture, right? So these are all of the geometries. I got all of the geometries for you, but you should be able to have them. I have all of them in a table for you to be able to tell me for any geometry that I give you, whether it has a pair or not. You should be able to tell me what is the electron geometry, then what is the molecular geometry, what are the angles, what is the name of the geometry. You should be able to tell me by just looking at the formula, because if I give you a compound, you now know how to draw the Lewis structure, and then when you draw the Lewis structure correctly, you will know if it has lone pairs or not, and then from how many things that are bound to the central atoms, you should be able to tell me what geometry it is. What is the molecular geometry? What is the electron geometry? What is the angle? Make sure that you know that. Very, very crucial. Now that we know how to do the geometry though, let's go to the next thing, which is polarity and dipole moments. So after you know how to predict geometry, then you use it to find whether or not something is polar, right? And we talked a little bit about polarity earlier, but I do really want you to understand, because this is going to be crucial, and it should kind of inform us why we're really doing this when it comes to doing geometry. Why? Because, so again, if you remember, polarity is an unequal distribution of charges in a chemical covalent bond. So if you have like hydrogen here bound to chlorine here, right? This is the Lewis structure. We know that hydrogen and chlorine are sharing these bonds. They're sharing this bond and these electrons. But we now know that they are not equally sharing. They are unequally sharing, and this is called polarity. Chlorine is pulling more than hydrogen is giving, more than hydrogen is pulling. So the polarity is going this way. So this is kind of partially polarized, right? So this is kind of like partially negative. This is partially positive, even though these are not charged, but there is an unequal distribution. And we call this a dipole moment. Dipole moment. So dipole, when I hear dipole, I think of magnet, right? A magnet has 2 poles, north and south, right? So the dipole means 2 poles in these molecules as well. So this is a polar molecule. This molecule is polar. Why? Because it has an equal distribution of electrons. So polar means unequal sharing, right? It's an unequal sharing of electrons. That's what polarity is. So after you draw the Lewis structure and you see the difference in this bond, then you know that there's polarity. And what matters and what influences the polarity, by the way, is the electronegativity, right? The more electronegative an atom is, the more polarity there is, right? The more electronegativity difference there is between the two atoms, the more polarity it is. Does that make sense? But we're making it too simple because we only have two atoms here. But what if you have three atoms, right? How are we going to know the polarity? So if you have some like, okay, CO2, if you remember how to draw CO2, right? It's going to be carbon, oxygen, and it's going to be pairs, electron pairs, right? So this is CO2. This CO2, if I come in here and ask you, is this polar or non-polar, right? You might be like, oh, okay, I know that polarity is an unequal distribution of charges, and oxygen and carbon have different electronegativities, so there's polarity here, so CO2 is polar. But I'll be like, no, that's wrong. There is polarity between carbon and oxygen, that's true, but there's another polarity between this carbon and oxygen that's opposite and equal. And guess what happens to forces that are opposite and equal? They cancel out. They cancel out. So CO2 is non-polar. Is non-polar. Why? Because the polarities cancel out. Right? So when you have an unequal sharing of electrons here, right? So level one is, if you have an unequal sharing of electrons, you have polarity. Level two is, if those unequal sharing of electrons cancel out, then there's no polarity. That's level two. Level three, though, is that if you have, right, so let me give you an example. Let's say water, right? H2O. H2O is oxygen, hydrogen, but now that we know geometry, we know that there's a bent, right? There's a bent here. So if you ask you, is H2O polar or non-polar? You'll be like, oh, okay, between hydrogen and oxygen, there's polarity because oxygen is more electronegative. So there's polarity here, and then there's polarity here, right? So this is the next level, because look at this. Because the geometry is bent, they will not cancel out. They will not cancel each other because one is going this way, the other one is going this way. They are not opposite. They are equal, but they're not opposite. So they will actually add up. They will add up. So that's why H2O is actually very polar, right? So this is the third level of measuring polarity, right? The first level is you look at the bond. When it's just two of them, just look at the bond, right? You see if there's an equal sharing, there's polarity. The next level is just look at if you have more than one atoms bound. You look at this, you see, yes, is there polarity in the bonds? Yes, but do they cancel out? If the answer is yes, there's no polarity. So another example of this, by the way, is our friend from the beginning, right? CH4. So So our friend from the beginning, CH4, is going to be like this, right? It's going to be carbon, but as we learned earlier, it's carbon and 4 hydrogens, and it's a tetrahedral, right? If you remember, so they will cancel out. They will cancel out, and CH4 will be non-polar. Now, if you are following me, which I think you are, I'm going to give you a challenge. I'm going to ask you a question, and if I was in class, this is what I would ask, and wait for somebody to answer me, right? So if instead of having CH4, I replace one of the H's here with chlorine, for example, right? So this is a real compound called CH3Cl. If I do that, do you think this is polar or non-polar? What do you think? Is there polarity in the bonds? Yes, there is polarity in the bonds, right? So when do they become non-polar? Is when they cancel out. Do you think these are going to cancel out? No, right? They're not going to cancel out because this is not equal to these, right? So CH4Cl will be polar, even though CH4 is non-polar. All right. And again, the next layer that we added was when the geometry doesn't cancel, right? Then there's polarity. And to just give you a very quick hint, going back to the table, right? Whenever there is a lone pair, geometries usually don't cancel out. Whenever you have a lone pair somewhere, things don't cancel out, except this one. This one is a, look at this one. This one is when you have 3 lone pairs. You have 3 lone pairs, and then you have 2 things bound. So this ends up being linear. So this one is going to be, it's going to cancel out. It's going to be non-polar. But usually whenever you have lone pairs, things don't cancel out. So a lot of things that have almost everything that has lone pairs will be polar. Okay, so just to recap, remember, right? You can, we're going to talk about that later, but make sure that you can, if you get a Lewis structure, right? If you get electrons, you get Lewis structure, you can get an electron geometry and then molecular geometry, right? And then from here you can get polarity. So I'm going to talk about this next, hybridization, but you should get polarity, right? So why do we care about polarity? And this is an example of the polarity and whether, how things cancel out, right? So this is how things cancel out. But before I move to the next section, guys, I want you to give you something very important. Why do we care about polarity? We care about polarity because, did I say that water is polar or non-polar? Do you remember? We talked about why water is polar, right? So it turns out that in nature, there's a rule that you should remember that says that like dissolves like when it comes to polarity. Meaning that if something is polar, it will be able to mix with polar. It will be able to dissolve in polar. So things that are polar dissolve in water because water is polar. Things are non-polar, they don't dissolve in water. So that is why, for example, oil doesn't dissolve in water, but salt and other things dissolve in water, and sugar and things like that, because these are polar molecules. Polar dissolves in polar, non-polar dissolves in non-polar. Very, very important distinction, right? Things that are non-polar dissolve things that are non-polar. right? So like dissolves like. So when I give you a bunch of molecules, and then after I ask you the structure, geometry, the polarity, and all that stuff, I will ask you like, does this dissolve in water or not? And you will answer that based on the polarity. If it's polar, it will dissolve in water. Does that make sense? It's a very, very important take-home message that I want everybody to remember. Now, what I'm going to go to next is called hybridization, right? Hybridization. So what is hybridization? We learned about hybridization earlier, right? Because I want you to think about this, right? So in earlier chapters, you learned about how to represent nitrogen, for example, and oxygen and hydrogen. So remember that we say that hydrogen has one electron, so it's like 1 1. And then we say that, you can represent it in many ways, right? You can have hydrogen in the middle and then one little electron out here. But we learned that if you take it further and we really look into what's happening, we know that actually it's better to represent. Why is it going away? This dot is going away. But it's better to represent hydrogen by actually S and P and D orbitals. Do you remember those? Yeah, those are coming back. So this is going to be 1s1, right? So oxygen has, if I remember correctly, 16 and 8. It has 8 electrons, right? So the 8 electrons will be 1s1, because remember there are levels, right? 1s2. S gets 2, S gets 2 here, 2p. So you got 2 electrons here. So you have 4 electrons left. So you gotta add 4 electrons here. You guys remember those? So these are S and P orbitals, right? Nitrogen has 7 electrons, right? So nitrogen has 7 electrons. So it's going to be 1s2, 2s2, 2p3, right? So these are orbitals, right? And of course, as you can see, there are orbitals on the outer layer as well. So you have orbitals in the inner layer and then the outer layer, and the outer layer orbitals are the ones that do the binding, right? So the hybridization is taking this to the next level. What do I mean by that? Yes, you have nitrogen here. Yes, you have hydrogen here. But what happens to the orbitals on the outside? What happens to them when these two bind, right? Because guess what? The orbitals, this 1s1 orbital on hydrogen is going to hybridize with the orbitals on the outer layer of nitrogen. If you're making NH3, right? So NH3 is going to have orbitals of hydrogen and nitrogen hybridized together. That's why we call this hybridization, right? So if you remember, there were these weird shapes, right? The orbitals were these weird shapes. So the p orbital has this shape. So p orbital, if you remember, has 3 spaces, right? So the p has 3 spaces. That's like these, right? And you get electrons in these, okay? And then guess what? We're going to add hydrogen here. So when you add hydrogen, and we can hopefully this will help. Let's see. I think this will help. So it's worth doing. It's worth doing to see if I can help you understand this even better, because sometimes this gets people, but when we spend time with it, tends to become clear. So nitrogen, so we said the nitrogen, right, has on the outer layer, let's just do the outer layer, right? The outer layer of nitrogen has 2 orbital and 2p3 orbital, right? So it's like 2 2s2 2p3, right? And then hydrogen has 1s1, right? So if you remember, if we put them in a box to kind of represent what's in there, one box will have 1s2, and then one box here, so we'll have 2 here. And then if you remember, p has 3 spaces, right, where each box gets 1 1 1, and then you get extra, you have pairs. So with that, I want you to realize that this orbital has 3 spaces, right? 3 empty spaces. And guess what goes into the 3 empty spaces? Is these single ones, right? That's why you have NH3, right? That's why you have NH3, because you have 3 spaces here that go here. So we're going to hybridize, and guess what the hybrid is going to do? The hybrid is going to make this new box, right, where these S are going to come down and go here. So this will be a hybrid orbital of electrons from N and from H. So it's a hybrid orbital. Does that make sense? So that's a hybrid orbital. So these are what we're going to see, and you can do it with CH4 as well, right? So this is sp. I'll talk about that in a minute, but this is CH4. CH4 as well. We can hybridize, right? So if you remember, carbon has 4 electrons on the outer layer, right? So carbon has 4 electrons on the outer layer, and if we were to do them on the hybrid thing, we are going to, how many atoms does carbon, how many electrons does carbon have? Because you're going to have to do this yourself, remember? So if you remember, carbon has 6 electrons. You will have in a periodic table that will tell you. And the 6 electrons in carbon, right, will be, the first one will be in S, right? And then the next one will be another set of S. And then the next one will be P, right? And p orbital, since you have 6 electrons, you already have 1 2 3 4, right? So then 1 2 3 4, so then another one is going to be 1 5. What? You see it just disappear. All right, so we have these, right? And then in here, we're going to bring in, so let's say you have hydrogen, right, that has 1 electron. Guess what? If you were to make hybrids of these, then you're going to take a hybrid of p orbital into s orbital, right? So and so just to give you an idea, s orbital in real life, in real geometry, s orbital looks like this. P orbitals, the 3 p orbitals look like this. So if you make hybrids, they make a weird shape like this, right? Again, you don't have to remember or have to memorize the shape, but this is to show you how they look like, right? These are weird shapes of this hybrid orbital. So it kind of combines to show you this. And this, by the way, is how we make that tetrahedral angle, right? So it's all coming together. This is how we make that tetrahedral angle. But these orbitals, we call them sp3 orbitals. And this is very significant, right? This is very significant, sp3 orbitals. So I need you to be able to tell me what type of orbitals it is. So sp3 orbitals, how many things do you think are in there? Some people think it's 3, but it's 4. right? Because remember, S is also occupies space, right? So if you take S and P3, that's four things. Why does that matter? Is because, look, depending on the number of electron domains or things bound to the central atom, you should be able to tell me the hybridization level, right? So if you have two things bound to the central atom, it's sp orbital. If it's three things bound to the central atom, sp2 orbital. And you'll see how it's also similar to the electron geometry and molecular geometry, because it's all connected, of course. But I want you to really realize this, right? So four things bound to the central atom, sp3 orbital. But if you remember, after sp3, what do we get? It's d. So five things, sp3d, six things, sp3d2, right? But I want you to see something very important, right? When it comes to hybridization and finding the things that are bound to the central atom, we don't care whether or not it's a lone pair. We don't care whether or not it's a lone pair. It's a very important distinction. What do I mean by that? Let me show you. So I can ask you, what's the hybridization level of, for example, CO2, right? CO2. What's the hybridization level? The way you're going to do it is going to be like, okay, if you remember, we drew CO2 like this, right? And if we do CO2 like this, and then how many things are bound to carbon right now? How many things are bound to carbon, right? If it's two things, if you remember, two things is what? It's sp. How about water? Oxygen, hydrogen, hydrogen, right? I want you to pay attention. How many things are around oxygen here? Even though it's two atoms, but you also have two pairs. We still count them when it comes to this. So water is bound to four things and it's sp3. So remember, if you remember, electron geometry counts the pairs. So hybridization level also counts the pairs. All right? So far, we've learned about Lewis structure, geometry, angles, polarity, solubility in water. But now we just talked about hybridization level, right? And they're all connected. They're all connected, right? So we gotta know the hybridization level. But I want you to show you something a bit different though. And I kind of encountered it here in CO2, because CO2 is a bit weird. You realize that you have more bonds. And what ends up happening, if we look at, not CO2, but let's look at CH2. This is ethylene or ethene, right? So if we look at it, right, you see that if we have carbon, right, let me draw it to kind of give you an idea, because here they just jump into it. So look at carbon bound to carbon, right? What if instead of a single bond, it's a double bond, right? Like this. What ends up happening is you get different types of bonds, right? So you have the normal regular bonds, right? Like hydrogen and carbons, but then you have another bond that kind of overlaps here, right? So the electrons above and below of the bonding atoms also connect. So again, it's a physical thing. The hybrids are going to connect. So this is another way to show you, right? So these hybrids are going to connect on the top and the bottom, and we call this a pi bond. It's a pi bond, right? So the other bonds are called sigma, but this one is called the pi bond. So a double bond is going to create a pi bond. The pi bond is a spatial type of bond that occupies this weird shape at the top and the bottom, but this is a pi bond, right? Want you to remember that it's a pi bond, and it's a double bond, and we can also do triple bonds as well, right? So I'm going to give you, for example, a chemical, and then I'm going to ask you like, hey, in this chemical, which one is pi bond? How many pi bonds? How many sigma bonds? And in order to do that, you're just going to count the single bonds, and I want you to pay attention to this, right? The single bonds. So I'm going to count this one, this one, this one, this one, this one, this one. These are all single sigma bonds. But in the double bonds, remember that there is one sigma bond and another one pi bond, right? So if I were to count the sigma bonds, this would be 1, 2, 3, 4, 5, 6, 7, and then one bond here out of the double bond is going to be a pi bond, right? So here you have 7 sigma bonds and 1 pi bond, right? So I'm going to ask you how many sigma bonds, how many pi bonds, and you just have to count and look at the double bonds. Does that make sense? All right, so that is very good. That is very good. I think we understand now the sigma and pi bonds. We should understand hybridization. One more thing that I want to talk about is how does this show when we make diagrams and boxes? What do I mean by that? I want you to stay with me here, because again, this is another thing that tricks people, right? But I want you to get the right idea. And the right idea is this. So if you have let's do, it's an easy one. Let's do oxygen and nitrogen, right? We can do, let's do, yeah, oxygen and nitrogen is okay. But let's just do the outer electrons so that we don't have to draw all the electrons, right? So because the outer electrons are the ones that bind. But again, if you remember, oxygen, the outer electrons will be S2 and P4, and then for nitrogen, the outer electron is going to be S2 and P3, right? So if we were to represent them in box form, right, in those box diagrams, let's represent N and O in those box diagrams showing the electrons and their levels, right? So we say that it's going to be S, right? So S, let's say S has 2 electrons, and then it's going to be P that has how many electrons, if you remember? It's going to have 1, it's 4, like we say 4, right? 1, 2, 3, 4. All right. And then nitrogen is the same thing, but you say S is 1, 2, and then and then it's 3, right? 1, 2, 3. That's P, right? So again, just like hybridization was like how the shapes get together, right? We also need to know how these electrons also get together. And also, as you can see, I put them in different levels because these represent different energy levels, meaning which one gets filled first, which one gets filled later. Right? So these are energy levels. And then these energy levels, right? So if you have like a 1s electron here, right? 1s electron here on this atom and the 1s electron here on this atom, we represent these energy levels by showing how they add together to make a sigma bond. However, And I don't want to complicate this to you, okay, for you. I don't want to complicate this for you, but I want you to remember that we we treat how these electrons bind by something like how do I say this? Like a wave, meaning that they can combine to give you this bond, but if they are opposite, they can cancel each other out, what we call destructive interaction. So sometimes they get together and they destroy each other, whereas when sometimes they get together and they make an actual sigma bond. So for each bond we have an anti-bond, but don't think about it too much. That's it. This is some quantum physics type of thing, but just keep in mind that you have a bond, an anti-bond, and where it comes from is the fact that electrons, right, if you think of them as a wave, two waves, just like on an ocean, by the way, two waves, right, two waves can get together and make a bigger wave, or they can get together and cancel each other out with no wave depending on their direction, right? So this is what we call constructive versus destructive interaction, right? But don't think about it too much. Just know that we have a bond and anti-bond with energy levels. Okay, so here again, let's say you have an atom that has one s is going to bind here, make a sigma. If you have more, they make an anti-bonding, right? If you have more, they go here. If you have more, they go here, and so on and so forth, right? So you take the atoms from one molecule on one side, atoms from the other molecule on another side, and then you add them together with the right level, and then you can show the energy diagram. So this is how it usually looks like. Okay, you bring the first atom, you bring the second atom, and then you set them up. So again, these, I want you to be careful here. The ones in the middle are going to be set up like this, right? They're going to be set up like this, but this, this one starts at P. I don't like that this one starts at P. Let's go to the one which starts at S and then it goes up to P. Because if you have S, you start with S, right? So if you have S, they get together. If you have P, they get together, right? Still with me? So here, let's say you have one atom that has one atom that has one. Or let's say one atom that has two, yeah, that has one. Guess what? They're going to combine and make two here, right? If they have both have four, guess what? The next two are gonna go here. Does that make sense? And you will run out. Same with P, right? They are going to get on the P level. So you should practice doing this for different atoms, but I gave you some of these, right? So let's say you have these ones. Usually we will not complicate it, but if you have O2, if I give you O2, what am I saying? If I give you O2, what am I saying? I'm saying that oxygen that has S. So if you remember, oxygen has, we already said that oxygen has 2S and 4P. Do you remember that? 2S and 4P. Let me see if I can delete these notes that I added. Very good. All right. So you remember that oxygen has on the outer layer of oxygen, you have 2S. And you have oxygen on either side, so it's okay. You have oxygen on either side. So 2S and 4P. So we say 1, 2, 3, 4, right? And then there's oxygen here, 1, 4, 1, 2, 3, 4, right? So the question is, what's the orbital for oxygen? Well, it's going to be right here. 2 are going to occupy here, but you have 2 more because it's 4, 2, and then you have, so for P, for one side P is 1, 2, 3, 4. The other one is 1, 2, 3, 4. So it's 8. So I'm gonna fill up 8 in this order: 1, 2, 3, 4, 5, 6, 7, 8. Right? And that's O2. Oxygen here, oxygen here. If you go back here, you see that that's how they fill up. So you should practice with all of these. But in addition to giving you oxygen, again, remember, I can give you on this side, I can give you N, right? And that's okay, right? I can ask you how N and O bind. So I can ask you, how do N and O bind? And then you'll be like, oh, N, if I have N here and O here, I will remember that oxygen is 1, 2, 3, 4, 5, 6, right? And then here on the outer layer, remember that for N is going to be 1, 2, 3, 4, 5, right? So then you're gonna be like, oh, S is 4 electrons, 1, 2, 3, 4, and then P is 1, 2, 3, 4, 5, 6, 7 electrons, right? So it's 1, 2, 3, 4, 5, 6, 7 electrons. So this is the representation of NO. Does that make sense? So you should practice how to do this, the molecular orbital or configuration, we call it. So if you want to Google some practice, just Google molecular orbital configuration of blah blah blah, or molecular orbital configuration practice. But that is about an hour, and that is a very, very good place to start. But I really want you to take time. This is a video, so you can always replay it, and of course ask me questions when you need them. But this chapter went further in exploring chemical compounds, and we looked at how chemical compounds are not flat. They're 3D, so you should be able to set up the three-dimensional structure of them based on the central atom and how many atoms are bound to it. But we also learned that lone pairs also make a difference. So I think I talked about 10 different geometry names that we need to remember, but again, it has to come from the right Lewis structure that we've drawn up. So if I give you a compound, a formula, you should be able to draw the Lewis structure, and then from there give me the geometry, and then we learn that from the geometry we get the polarity, and then from the polarity we get the solubility in water or non-polar solvents, and then from there we also learned about hybridization levels, we learned about pi and sigma bonds, and we finished by these molecular levels or molecular energy that we call the molecular orbital organization. And these are very crucial and fundamental in chemistry and help us understand chemicals, especially when we get to the next level of performing chemical reactions. But that is enough for today, and I will see you in the next chapter. Bye-bye.